Good morning guys, welcome to today's worked exam answer video. Today I've opted to have a look at this AQA question which encompasses a little bit of transition metals followed by some reactions of metal ions in aqueous solution, which has also got a few bits of the transition metal stuff sprinkled into it as well. So I thought this was a really good question to show you guys because I can go through quite a lot of content with you, but I can also show you how, especially with these schematics here, they will bring in sort of the ligand substitution side of transition metals along with the precipitation reactions of the reactions of metal ions and aqueous solution topic and kind of merge those together. It's also got a couple of really common questions that get asked about colour in terms of it being able to explain why something is coloured, do some calculations and state things that affect the colour of a transition metal complex. So I guess quite a few reasons why I opted to choose this question. Now we're told at the start it's about copper-2 complexes, and we are told that the colour is caused by the d electrons of copper moving from their ground state to an excited state. And normally that is a line that you would need to include in your explanation for explaining why a particular solution is coloured, whether they tell you exactly what colour it is or whether they just say explain why it is coloured. That would mean that this kind of question is usually worth 3 marks and here it's only worth 2, and that is because you don't need to give that sentence in your answer because they've already given you it. However, if they didn't, that would be the middle point that I would want you to make. Now, we can see that they've told us the colour of these ions. Now, first of all, these being yellow might surprise you because hopefully we're aware of the fact that most copper things are blue or some variation of blue, but CuCl4 2- ions are yellow, and I'll come back to why that is so different when we have a think about part C of this question. But the bit that's relevant for now is if we are told the colour of a solution or we're expected to know the colour of a solution, we need to build that into our explanation here. So we can't just say, oh yeah, visible light is absorbed, the d electron is excited from the ground state to the excited state, and then the complementary colour is reflected or transmitted. We need to link it in with the fact that it's yellow. So the yellow is the colour that is reflected or transmitted, meaning that it must be sort of blue-purple light that is absorbed from the visible light part of the electromagnetic spectrum. So if there is specific colours involved, you have to be specific in your answer. So part A, CuCl4 2- ions are yellow because, and I'm saying blue/purple because they tend, even though we do need to be thinking about our kind of colour wheel and complementary colours, they tend to stick to the more primary colours when we're doing this, because strictly yellow and purple are our complementary colours, but I think they'd be kind of happy with either of those because blue is a bit more of a, well, it is a primary colour compared to purple, because blue, purple, light from the visible light part of the electromagnetic spectrum is absorbed, and that does the promoting of the electron from the ground state to the excited state, which is what you would write next if we hadn't already been told that. And therefore yellow, which is the complementary colour, is the one that is reflected or transmitted, and you can say either, don't need to say both. I'm going to include both so that you know either is okay. Bless me. So yeah, one for saying that the blue-purple light is absorbed, and then one for saying that it is the yellow that is reflected or transmitted. Hence, we see the solution as yellow. Okay. In terms of calculations, it might be that we are asked to work out the size of the energy gap between the ground state and the excited state. So we're thinking about when we promote the electron, how separate are those different d orbitals in the ground state and the excited state, and the size of that energy gap determines what frequency or wavelength of visible light is absorbed, and thus subsequently what colour is reflected. Now, the formula for being able to work out the energy gap, delta E, is equal to Planck's constant, which has lowercase h, and then it depends on whether you're given the frequency or the wavelength, or whether you're trying to work out the frequency or the wavelength. So we're wanting to work out frequency, which is the weird V, the Greek letter with the V shape. And again, just for your context for this video, if you are given wavelength, you will also be given the speed of light, and you would do Planck's constant times the speed of light divided by the wavelength. We don't need to do that, so I'll put that in brackets here. Now, we're not actually wanting to find the energy gap in this question. They've given us it. Energy, joules, and then Planck's constant, because it is a constant, will always be given to you. And frequency should always be in seconds to the -1. And the units can also help us to figure out this equation if we happen to forget it, because if the energy change is in joules and Planck's constant is in joule seconds, frequency has to be in seconds to the -1, so that the seconds and seconds to the -1 cancel to leave us with joules. So frequency, therefore, is going to be equal to delta E over H. So nice simple calculation really. 3.98 times 10 to the -19. Don't know why I've not been using my ruler. Sorry, it looks messy. And then Planck's constant, 6.63 times 10 to the -34. Pop that into my calculator. Into three significant figures, because that's what the other values in the question are given to. That's going to be 6.00 times 10 to the power of 14 seconds to the -1. Okay. State 3 ways in which a transition metal complex can be changed to alter its colour. Now, these are things that you can rote learn. There's only really 4 things that we can change, and one of them, I guess, is not really wanted in this type of question, but if we change the transition metal itself, for example, if I changed it from copper to iron, that's going to change the colour of the transition metal complex. But the 3 that they're more interested in is 1, the oxidation state of the transition metal. So copper 2+ ions are coloured, either blue or, in this random case, yellow. If we had copper 1+ ions, they wouldn't actually show colour, because there is a full 3D sublevel, so we can't promote any electrons from the ground state to the excited state, so that clearly shows a massive effect of oxidation state. Probably the most common one to think about is iron 2+ and iron 3+, of which iron 2+ complexes are green and iron 3+ complexes are brown. So that's one thing. Second thing is the ligands that we have attached. And again, we'll see the effects of that in the latter part of this question. It's not just, are we thinking about like chloride ion ligands or water ligands, which are both monodentate ligands. If we have monodentate versus bidentate, or monodentate and we swap them for multidentate, that can affect the colour as well, because that will affect the size of the energy gap. Then the third thing is the coordination number, which is the number of coordinate bonds that the ligands are making with the transition metal in the middle. So if you've got 4 coordinate bonds, the coordination number is 4. The coordination number of this CuCl42- complex is 4. If we have 6 coordinate bonds, then that would be octahedral. So coordination number is heavily linked with shape. And if we change the shape, because we change the number of coordinate bonds, that can have a big effect on colour as well. And when we think about this complex being yellow, there's 2 things that are really going on here. We've swapped sort of water ligands, which copper with 6 water ligands would be blue. We've changed the ligands to Cl- ions, so we've affected this middle point. But also by swapping those ligands as we have done, we've also changed the coordination number from octahedral to tetrahedral, or rather we've altered the coordination number from 6 to 4. So we've changed 2 of the things in here, which can help to explain why that is yellow when most copper things are definitely not yellow. Okay. And now if we think about this reaction scheme, we're starting with the yellow, CuCl42-. We're adding an excess of water to make P, and then from P we're making R by adding Na4EDTA, and this is where the transition metal part of this question comes in, because EDTA is a multidentate ligand, and we need to know that EDTA, or 1 molecule rather of EDTA, can form 6 coordinate bonds, and that's going to help us to identify complex ion R for the last part of this question. We've also got excess aqueous ammonia being added to make Q, and we can see that Q, R and P, sorry, I don't know where S came from, are all solutions. So not only do we need to know what happens when we add ammonia to this, we need to know what happens when we add an excess of ammonia to this. And basically the remaining questions are all thinking about this schematic. So I've kind of already nearly given away part D. Name the shape of the CuCl42- ion. So we've said it's got a coordination number of 4. There are therefore 2 options for what shape it can have. It'll either be square planar or tetrahedral, because both of those have 4 coordinate bonds within them. The general rule is, if your complex has a charge and if it contains chloride ion ligands, of which both are true here, then it will opt to have a tetrahedral shape, whereas if it contains platinum as its transition metal and or the overall charge on the complex is neutral, it would be square planar. So your chloride ion, complex ions, tetrahedral. Okay. Part E. Give an ionic equation for the conversion of CuCl42- to complex ion P. So we want to be thinking about what's going on if I add water here. Now, this is kind of both a reactions of metal ions and aqueous solution question, because we need to recognise that we're going to make the aqua copper ions. That's what P is. But we can also think about that from a ligand substitution point of view, because the water ligands will swap with the chloride ion ligands. So for our ionic equation, we will have CuCl42-. We're going to need 6 waters, because we need to appreciate that the water ligands are smaller than the are smaller than the Cl- ligands, so we can fit 6 of them around the copper. So it'll be CuH2O 6 2+, and then the 4 Cl-, which we have substituted the waters for. Now it doesn't ask for the colour of this, but I'm going to give you it anyway because it's good extra revision. This is a blue solution, and you will be expected to know that for the reactions of metal ions and aqueous solution topic. The other thing that I maybe should have done here, instead of using a forward facing arrow, not that I'd be penalised for it, but this reaction is reversible. So we do need to be aware of the fact that if we did start with this, we would add 4Cl-, which would come from hydrochloric acid, and that's going to change the coordination number, of the complex, and then we'd get a colour change from blue to this, which is yellow. Okay. Part F, state the colour of the solution containing complex ion Q, give an ionic equation for the conversion of this to Q. Now, this is an interesting one because even though we start with CuCl42-, because we add an excess of aqueous ammonia, the first thing that will happen is this. We will generate these hex aqua ions in solution. Then we kind of know what's going to happen when we add ammonia. The ammonia will act as a base initially, and it will take protons from the water ligands, and we'll end up with a neutral blue precipitate. But because we're adding the excess of aqueous ammonia, we then get the partial ligand substitution reaction, which again we need to be very much aware of, which generates a deep blue solution where we have 2 water ligands and 4 ammonia ligands as a part of that complex. So, in terms of writing the ionic equation, we are going to have to start with the CuCl42- ion, which is a little bit odd, like I say, because when we're thinking about this from a reactions of metal ions and aqueous solution point of view, we'd be thinking about going from here, but these hexa aqua ions would definitely be formed on the road to generating Q. Now, if I was therefore writing an ionic equation for this, the bit that I would want you to, I guess, remember is that when we think about adding an excess of aqueous ammonia to copper ions, this is the formula of the complex that is made. And this is an example that we need to know because there aren't that many examples of partial or incomplete ligand substitution, but that's what's going on here. And also, this complex can show cis-trans isomerism because it has 2 different monodentate ligands in the ratio of 2 to 4. So we can put the water ligands 180 degrees apart, trans isomer, or 90 degrees apart, cis isomer. And so thinking about that as our product complex ion, we can then use that to go, right, well, I'm going to need to add 2 lots of H2O in order to get the 2 water ligands in there, and I'm going to need to add 4 ammonias. And then I'm going to generate this as my complex ion, and I'm going to need to get rid of the 4Cl-. Notice how I didn't try and write the reactants in until I'd thought about what the product was going to be, and then that made it much easier for me to go back and add in those other reactants. Okay, if we were doing that from here and we were making this, we would just need to go from here, just add 4 NH3s, we'd get this, and 4 of the waters will have been substituted out. Okay, so this is a deep blue solution or a dark blue solution, whichever you prefer, but we do need to distinguish it from the hexa aqua ions, so don't just call it blue, it needs to be a deeper blue than this one. And again, that comes back to this, the only thing we've changed is 4 of the ligands, but in changing 4 of the ligands, the frequency of the visible light that has been absorbed ever so slightly different, hence we get a deeper blue solution, because that deeper blue colour is reflected or transmitted. Okay, And then finally, identify complex ion R. So you've kind of, I guess, got to be semi-aware of what P is in order to be able to figure out what's going on. But equally, if we know that we have EDTA as our multidentate ligand that can, with one molecule, form 6 coordinate bonds, we're only going to need one EDTA. We know that we're dealing with copper as our transition metal in this question. So therefore, we're going to have copper, we're going to have one EDTA. And then we should really be aware of the charge on EDTA, but in this question, they've given us the opportunity to work it out by telling us that we're adding Na4 EDTA. So if each Na is +1, EDTA therefore has to be 4- as the charge on that ligand. And then if I've got a Cu 2+ ion and an EDTA 4-, that is going to give me Cu EDTA 2-, 2+, 4-, 2- overall, and that would be R. With a lot of these, rather than rote learning the equations, it's good to know what type of reactions are going on, and also the idea that, for example, if we started with this and we just added a normal amount of ammonia, or we added it dropwise, that we would get the precipitate of CuH2O4 OH2, and being able to recognize that that's what's formed based on the charge on the complex, what the ammonias are acting as, which is a base, they're taking protons away, and that the reason why we stop at 4 waters and 2 OH- is because that's when the complex is neutral, so it precipitates out of the solution. If we understand those ideas, it takes away a lot of the rote learning for that aspect of the topic. But hopefully that's been useful. Let me know if there's anything that I've said that's unclear, if there's anything I can clarify, if there's any similar questions you want me to go through. And as always, thank you so much for your support. I hope you're all doing as well as you possibly can be, and take care of yourselves. Catch you soon, guys.